So today I'm going to talk about some of what's changing in the Arctic. I think you're probably all aware that the Arctic is one of the areas on the planet that is showing some of the most rapid changes in response to global warming. And it's been a lot of the news in a variety of ways this past summer. Dramatically, a few weeks ago with the emergence of Crystal Serenity, the largest passenger ship to have ever attempted a transit of the Northwest Passage. Got about 1,600 people on board. Some of them paid as much as $120,000 to ride this luxury liner. And of course, they started in Seward, but through the Bering Sea, and of course, the Northwest Passage is the route they transited here. They arrived just recently in New York. And many people were very concerned about this venture. That is, anyone who has responsibility for search and rescue in this area was concerned. They're moving through water which is without ice right now. It's not an ice-strengthened ship, but it's also water that's very, very poorly charted because it's been covered with ice and a remote area that few people have really transited. And of course, it also brings to mind the first transit of the Northwest Passage by Roald Amundsen, probably our greatest polar explorer, first to the Northwest Passage, first to attain the South Pole, also transited the Northeast Passage, and a number of other major accomplishments. Probably first person over the North Pole, but he was in a dirigible because others who claimed to have gotten there on the surface probably hadn't. But Roald Amundsen transited the Arctic Northwest Passage in 1904 to 1903 to 1906. Took him 3 years. Now, there are various routes to the Northwest Passage. The one that the Crystal Serenity took, this is the coast of Alaska here, through this area close to the continent of North America, this archipelago, of course, the Canadian territory, is through which one moves to find the Northwest Passage and emerge here. The Crystal Serenity followed the same route. Amundsen, actually Crystal Serenity came through here. Amundsen went this direction. You probably also saw something in the news the last couple of weeks about the discovery of the second ship of Sir John Franklin, his expedition in 1847, 1845. All the men were lost. The ships were found right in this area. But Amundsen, in this next slide, you can always tell, you don't have to look for the Cyrillic, you can always tell Russian charts because Russia is here and North America is here. But Amundsen transited the Northwest Passage with this route. Again, it took 3 years, the dates are on here. He actually made it through the passage, but had become frozen in the Chukchi Sea. So at this point, he hopped off the ship and skied 500 miles to Eagle, what's it called? Eagle City, I think, in Alaska to telegraph that he had made it through. Then he skied 500 miles back to the ship, and the following season made it out. So this took 3 years. It took him 2 years to do the Northeast Passage. So not only has the Crystal Serenity done something extraordinary this summer, even more extraordinary is David Hempelman Adams, during the summer, transited both the Northwest and the Northeast Passage in one season. So people who think that the Arctic maybe hasn't changed a lot in the last century, or maybe we're in the middle of some little cycle in the last 20 years or so that could reverse, we of course know that now with very good records back, certainly at the time of early explorers in the mid-1800s, early 1800s, late 1700s, that we've never seen the Arctic open like it is today. So David Hempelman Adams in his 15-meter yacht made this in one summer season. This is an image from the early 90s in the central Arctic region. On an icebreaker looking forward, you see another one in front here, out a half mile or so. And this very thick ice being broken up and turned over And of course, there are people, including a Secretary of the Interior a few years ago, who referred to this whole area as a vast white nothingness. But what's a little appreciated, people who haven't really studied the Arctic, is how the organisms that live within the ice and under the ice include photosynthetic algae. So there's a food web that actually develops within the ice. And changes that are now occurring in the Arctic with the loss of ice are certainly going to affect this food web. Because the primary production that drives this food web derives from this community of microbes in the ice. This is a cartoon we used a decade or so ago for Arctic climate impact assessment. And the point of this cartoon is that all the organisms that you see with large images here, fish and invertebrates and mammals and birds, are in some way uniquely linked to the Arctic. These seabirds maybe spend only part of the time of the year, part of the year there, but it's where they have their major reproductive event, so it's critical to them. Others are year-long residents, like the polar bear and the seals and the walrus. And of course, if you look under this ice, you see this little green cloud here. This is the primary production, the algae, which are a part not only of the underwater environment, but also the ice itself that fuels this ecosystem. If you didn't have the unique habitat of the sea ice, which is a concern about the future, this food web would be very different. The seals that you see here don't have a terrestrial alternative. They build dens on the ice, snow that covers the ice to birth. They live entirely on or under the ice. The food that they need is only in sufficient concentration right under the ice. The seabirds actually feed at the edge of the ice where it's melting, where there's a substantial bloom of plankton. Mentioned in this picture is the walrus. Another cartoon shows the walrus here. You might think it only dug around to the bottom, which it does, of course, to eat mollusks in the sediment, but the walrus also needs the ice. The young walrus in particular, after they dive with their mom, come back to the surface, they need to rest on the ice and recover from the diving experience. And again, here you see this green cloud, which you see it tinges, more about this later, over into the region of the ice. So you have a large bloom right at the edge of the ice, but what's happening in and under the ice is an important part of the story. And this looks like a bearded seal, but the major prey of the polar bear is the ringed seal. And it's the most abundant seal in the Arctic, and as you can see from this image, it's rotund. It is an absolute ball of blubber, and if a polar bear captures a ringed seal, or when it does, I should say, the first thing it does is to with its claws, actually tear open the skin and eat the blubber. Because if they were to be scared off of that kill, and the musculature was still there, the skin was still there, which they will eat, they would have gotten the most nutritious part. So the thick layer of fat, it's absolutely essential for the female bears to acquire this lipid during the summer, or they would not be able to reproduce in the winter. Basically, they stop eating at the end of summer. They give birth to a couple of cubs that 2 or 3 that weigh about 1 kilogram. In the late autumn, she doesn't eat, she doesn't drink. In the spring, those cubs weigh 10 kilograms. They come out looking like little polar bears. They've lived entirely on the milk, which is derived from the fat that she stored during the summer. And of course, the walrus, iconic Arctic species, is also being stressed because, as you see, walrus gathering on these small pieces of ice, essential for their rest and recovery. Walrus don't go far offshore because they have to have a bottom that they can dive to harvest mammals, or harvest mollusks, excuse me. They actually suck the contents out of a mollusk. They don't break the shells. They have a very powerful tongue that will create suction and draw this. And of course, as I mentioned, there are several species of seabirds that in colonies that number in the thousands on a rock cliff like this, with no nest, just a little rock perch and an egg that is sort of pointed on one end so it won't roll off the ledge, it'll roll in a circle that starts to move. No nest material, mom and pop sitting on the egg, the other going at the feed, coming back, and then when the young hatches, both of them out to feed to nurture the young. So this is this is from that same period in the early 1990s. I'm in a small helicopter. This is a Russian nuclear power icebreaker. They painted a wonderful mouth on the front of this thing. These are the most powerful icebreakers in the Arctic. They can move through ice 3-4 meters thick and literally go anywhere they want. No other nation has this capability. But one of the remarkable things that I was really unprepared for the first time I was in the Arctic is no matter how thick the ice is, when you look off the edge of the ship, which is here, down at the ice, which is a few meters down, when it turns over, you see this greenish or brownish color. And my initial thought was, well, as we were in the thinner ice, but once you get into the thicker central ice, Arctic ice, you wouldn't see that. But you see it even with ice 3-4 meters thick. And so another example, and sometimes when these water will come squirting up between these broken pieces and moves this brown, green slurry up onto the surface of the ice. So the really important thing to keep in mind is how different sea ice is from lake ice or refrigerator ice. Because when sea ice freezes, it's the water molecules that are going from a liquid to a solid form, but the salt, of course, can't be part of that crystalline structure of the ice. So it's left behind in brine pockets or at the edge of the ice. So some of it is excluded, and the water next to the sea ice forming then becomes dense because it's as cold as you get without freezing. You just got to charge it salt, so it's going to sink. But that which is retained within the ice forms these brine pockets. And it's in those brine pockets that algae, which have a salt tolerance, and go from the seawater adjacent to the ice to these dense brine pockets, dense in terms of salt concentration in these brine pockets. And the reason it doesn't freeze is it gets saltier and saltier as you extract the water molecules to make ice around it. But over time, the algae, the bacteria, the protists in these brine pockets mature. And if you look at them under the microscope, the diatoms are very common. You see here, just sea ice under the microscope, you could see all this greenish golden tinge. And some of these diatoms under the ice can stream into these long filaments. Igor Melnikov is one of the Russian scientists who began some of the very first work in the early 1980s in the Arctic and the Antarctic to dive in winter and take these organisms back to the laboratory and culture them and study their properties. And now, of course, we know a great deal more about this. And as the ice breaks up then, as you look over time, with the ice melting, some of these brine pockets end up condensed into layers. We'll see others stream down through the ice. But as it breaks up, then it releases into the water the contents of these pockets, which then adds to the productivity right at the edge of the ice. So here you see material being included as the ice forms, and here it's being released. And again, if you look off the side of this is about a 2 meter thick piece of ice. Here's this greenish tinge on the other side. So these pockets, as I said, will over time condense and actually sink and drain down through the ice, as you see here, and is shown in this cartoon. But one of the remarkable things that, again, people didn't realize until sometime in the mid-'80s was if you go under the ice and take a photograph, these brine channels kind of work like a light pipe. so one of the questions, you have this thick layer of ice, you have snow on top, how on earth can you get enough photons down through that ice for photosynthesis to grow underneath? Well, here's how. So the transparency of these brine channels is how photons are being scattered through the ice, then end up being transmitted downward into the water below. And just as another little diagram, just one other factor, when the ice is melting, and you see the contents of these channels and pockets being broken up, released into the water, the meltwater also makes the surface area more buoyant, so it keeps them near the surface. So this is what helps enhance the success of this bloom right at the edge of the ice. So when ice is forming, you have dense water, it's sinking, but when it's melting, the buoyant, fresher water will stay near the surface and allows then the birds in particular, which are feeding from the air, ready access to the food living, their food, the species that are living in this seasonal marginal ice zone. Now, you're probably all familiar with the importance of the species of euphausiate shrimp, Euphausia superba, which is commonly known as krill in the Antarctic. There is no comparable crustacean in the Arctic, but there's a very small fish known as a polar cod, which serves the same role in that food web. So whereas the krill in the Antarctic is a very important form of food for the penguins, for the great whales, for crab-eater seals, more about that in a moment. In the Arctic, the seals and many of the other mammals, the narwhal, for example, will feed largely on these small polar cod. These are Paul Nicklin's wonderful photos of polar cod living right under the ice. And again, another Paul Nicklin photo from his great collection of euphausiids in the Antarctic. So again, in the Antarctic, and I'll say more later just in passing about the penguins, but penguins are a big consumer of the krill, certainly today. And another extremely important group of organisms that have historically been primary consumers of the krill are the great whales. This is the northern right whale, but the blue whale and the humpbacks, in particular, the sei whales in the south have been really, we'll see later, important parts of that ecosystem. And I also mentioned the crab-eater seal. It's one of the most common seals in the Antarctic, and even though I said it's called a crab-eater, it doesn't eat crabs, it eats the same krill. And here's our specimen from the Museum of Comparative Zoology at Harvard. Aren't those interesting teeth? They don't grind, they don't pierce, they filter. So the teeth have evolved to this interesting shape that allows the mammal to take a cup of water with euphausiids, squirt the water out, and euphausiids. So back to the Arctic. Here's our ringed seal, and because they need to range over a large area to harvest their food, they maintain breathing holes, and they have longer and sharper claws than any of the other Arctic seals. So they keep these holes open by working the edges of them. And as I mentioned earlier, they will make a den in snow on the ice for their young, and then the young will stay in the den. There'll be a breathing hole when the mother's out, a breathing hole right next to it. The mother will go to find food, come back to the young. This just a little interesting series of photos that we came upon this polar bear, and this is a breathing hole. This is surface meltwater. The ice is probably a meter thick here, but there's the hole. And we approached this bear very, very slowly on a ship. It's probably 20 meters out when the ship stopped. It was aware we were there, but after we stopped, it turned around and came up to take a look at us, but ultimately went back because it was more interested in the seal. So hope springs eternal, And you often see, these are cubs that are now they're in their second season, so this would be their second summer. They stay with the mother through the second year, and then they're on their own. And you'll notice that the second one here is a bit smaller than the first, and that's not unusual. And of course, now and then you do see a bear with a fresh kill, and how quickly they not only the kill is instantaneously, they crush the skull, but how quickly they can devour the carcass. This next was a bear that we encountered in the water, swimming, and just watched it and swam ashore, and then we found out why it went where it did, because you see the remains. There's the skeletal remains, the ribs here of a seal that it had been eating, and after the bear felt relaxed, didn't fear we were going to take its remains of food, it then stuck its head in the water and pulled the pelt of the seal out, which it was in water just offshore, and began chewing on it. Now, just a couple of brief comments about the contrast between the Arctic and the Antarctic. And it comes up not infrequently when people who are unhappy with some of what scientists are saying about how rapidly sea ice is changing in the Arctic and what a strong signal that is for global climate change, say, well, it's not changed so fast in the Antarctic, so how do you know? Now, of course, we have a very, very different situation in the Arctic with the Arctic Circle, roughly the dotted area here. You see that within the Arctic Circle, except for this part of Greenland, almost all the Arctic, the high Arctic within the Arctic Circle is an ocean covered with ice. This shows how shallow the shelf is. The light blue or light pale bluish green here is the continental shelf, and here's the deep ocean. And of course, the Arctic Ocean is the cul-de-sac of the North Atlantic. The exchange through the Bering Strait is very shallow. So most of the water exchange with the deep Arctic Ocean is with the North Atlantic. And so if we look at the contrast with Antarctica and the Antarctic Circle, see that the center of the South Polar region is occupied by a continent around which sea ice forms seasonally, but it basically, within a season, forms and completely melts. So you have very little in the way of multi-year ice in the Antarctic. Whereas in the Arctic, historically, that sea ice has remained in summer and accumulates over time to thick ice. This is an old CIA atlas which shows the extent of sea ice in the Arctic, and the white area here in the 1970s was meant to indicate where the ice is permanent year-round, and as you move out with increasing degrees of sort of stippling, move into areas where you'd have ice in the winter, but this would melt through time, and then some slush ice perhaps remaining in the summer. And the contrast in the Antarctic, of course, is that in the dead depth of winter, you can have sea ice that's roughly, if you integrate this area, comparable to very little remains in the summer. So there's not a lot to change in the summer in the Antarctic in terms of sea ice, whereas in the Arctic, where the air temperatures in the summer are just barely below or slightly above freezing, warm it up a bit, and water changes phase, goes from solid to liquid. So we have just passed the nadir, that is mid-September, for Arctic sea ice. So the maximum Arctic ice is in late February, early March. The minimum is in mid-September. And this shows the September value for 2016, which is slightly, it's arguably the second, but you might say it tied for second lowest year, 2007. Here's the lowest, 2012. And you see, of course, it's a very jagged trajectory, and what controls the loss of Arctic sea ice in the summer is not just temperature, but of course clouds. And the thinner the ice, the greater the role for wind. So as ice gets thinner and thinner, wind can, a summer with strong winds can move more ice out of the Arctic. A summer with less wind wouldn't move so much ice out. But if you look at the annual mean Arctic sea ice extent, that is, you average all months of the year, you see it's still an up and down record, but there's no question that this is a strong downward trajectory. And these are all based on the satellite data, which only start in 1979. So before that, we have lots of other records, everything from all the way back to the 1800s, from sealers and whalers and Hudson Bay and all the presence in the Arctic, most of it driven by commerce, kept track of these sorts of where the ice was at different points of the year. This shows what the Central Arctic looked like in the early 90s. That same ship I mentioned earlier, and these little the windows, if you wish, on the bridge about the diameter of about the height, the diameter of the dot, about 1 meter, and so you see this ice being turned up here is on the order of 3 or 4 meters thick, and by the early 2000s. It's actually the same ship, but for a period they had painted this wonderful mouth out. Came back on, but look at the thickness of the ice here. And this shows you what was really happening. So this shows the extent of multi-year ice. So in color here, the red is the ice that's more than 5 years in age, and it will accrete depth with each passing year. So 5-year ice might be 4 or 5 meters thick. 1-year ice is typically about 1 meter thick. And so if you look at actually the trajectory we were on, which was to go from Franz Josef Land to the North Pole, which about here you would have seen in the early 90s, late 80s, you would have been in a lot of 4 or 5-year ice. Whereas by the early, our case, the early 2000s, but mid-2000s, you can see that there's very little multi-year ice left in the Central Arctic. So part of the story that we all hear about is ice area shrinking, but an even bigger part of the story is how much it's thinning. So here, this shows ice thickness in 1979, again in color here, which is, in this case, these are actually, this is thickness in meters, so this is 5 meters. And notice that in 1979, when the satellite series began, there's a lot of ice here, and 3 or 4 meter out here, it's 2 or 3 meters. And by the time you move to 2015, we haven't seen 2016 data yet, September, here's what you've got. So there's a little multi-year ice here, but virtually nothing of substance over here. The area has shrunk, but again, we've lost thickness. So you look at ice volume, this little clever little diagram starts in 1979, winds around, it doesn't go beyond 2015 for some months here. But you see winter values, which are the months out here, summer values in here. The winter values now, we've lost about 40% of sea ice volume, but in the summer we've lost 80%. So these are 20% now of what they were in 1979. These are about 60% what they were. So we also have to keep in mind that this is not only disruptive for iconic megafauna that we tend to think about in the Arctic, seals and polar bears and the like, but it's also really upending the subsistence lifestyle of many people who live in the Arctic. And there are indigenous people in the Arctic all the way around, and all the Arctic nations, the polar regions. So you have indigenous people in the United States, indigenous people in Canada, indigenous people in Norway, Sweden, in Russia, all living within the Arctic, and in many cases highly dependent upon that environment for their food. And so communities like this along the coast of Greenland, there might be fewer than 100 people in a community like this, and yet they acquire very, very little of what they consume as food every year from the outside. It's harvested locally, of course, plant material, berries, but as you know, the diet is for indigenous people living in this area is very, very meat dependent. And people often wonder about nutrition. If you're eating fish and you're eating marine mammals, and it's not overcooked, you have plenty of ascorbic acid, so vitamin C, which of course we know was the plague of the early European explorers in the Arctic and sailors everywhere, because they cooked the meat to death. Vitamin C is heat labile. So ascorbic acid, in order for it to remain active, has to, you can't overcook the food. And of course, they dry a lot of their food as well. And in addition, historically and even today in much of the Arctic, dogs are still a major part of the provisioning enterprise. So sleds out on the ice with dogs, and of course you have to feed the dogs, not only during that season but the rest of the year. And a lot of that is done with the skeletal remains and skin and parts of the fish and mammals that humans don't eat. So here's the kind of predicament that we're in, where we have a system that we understand how it's evolved and how organisms are highly dependent upon the sea ice, and that food web that starts in the sea ice, that were it not there, you would still have plankton, you'd have plant plankton, you have animal plankton, you'd have a marine ecosystem, but it would be different and would not be the one that we know is successful in sustaining the mammals and the birds, the invertebrates that are so common in that area now. And so it would be different. We don't know how different. And so a lot of the effort today in trying to understand how the Arctic will change in the future has to do with the not only what's happening in water column, but of course a fair bit of this material makes it to the sea bottom, and that's where you have the rich fauna of invertebrates that, of course, nurture the walrus and other deep living organisms. This is an image from a year ago. Almost all vessels have tracking devices on them now, so you can see just where they are and keep track over time of what ship transits where. So in September a year ago, you see some traces through the Central Arctic. These would have all been research expeditions. You see some busy little crosshatched areas here and here, and down here, I guess, yeah. These are most likely geophysical explorations by the oil companies that are doing seismic surveys to see whether they might find reserves of fossil fuels that are worth their time and effort. Right up here off the coast of Alaska, Shell Oil was drilling a year ago. They decided not to drill the second well they had planned because the first one was dry. They spent $7 billion now drilling in the Arctic with nothing to show for it. But at some point, they will probably be back. Explorations off Russia continue. And of course, the Russians have also been opportunistic with regard to this route that took Nordenskjöld about 2 years to first transit in the Northeast Passage in 1879, 1880. Took Amundsen 2 years in 1920. Today, the Russians have commercialized this in the Northern Sea route and are escorting convoys of ships to shorten the route from Asia to Europe for commerce. And of course, the Russians are hoping to use their major rivers as other points of of commerce where they can move resources, timber and ores, out of northern Russia down the rivers and onto ships, which would be far less expensive than the situation they have today over vast different distances of land. All the major rivers in Russia flow to the Arctic Sea. The density of these lines, the darker they are, show just the degree to which they are being trafficked. So a thin little line somewhere would show maybe one ship. But these. So this raises another question about the Arctic. We know the Arctic is warming faster than the rest of the globe for a number of reasons, or at least a handful of good reasons. The one that is easiest to think about is just the albedo, the white snow reflecting 90% of white snow or ice, 90% of the incoming solar radiation back to space. Open water or bare soil or even soil vegetation will absorb more of that incoming radiation. Open water will absorb about 90%, whereas the ice or snow will reflect 90%. So that warms the water, melts more snow, melts more ice, warms the land, melts more snow. But if we look at what are argued to be the contributing factors to the radiative forcing, as we call it, and you look at a global average, you see the role of CO2 and ozone and methane, and you see this thing that here says BC, that's not Boston College, that's black carbon on the snow, and this is black carbon in the atmosphere. So soot, small particles of soot in the atmosphere also warm the atmosphere, and if it falls on the snow, it has that same absorbing albedo effect. The dark object on the snow will absorb more of incoming solar radiation and melt snow. But then look at the Arctic, and you see that black carbon has a disproportionate role relative to the global average. And unfortunately, there are no regulations right now with regard to the kind of fuel that ships use in the Arctic. We can argue no one is being more responsible than the Russian nuclear ice-breaking fleet in terms of greenhouse gas emissions in the Arctic. Basically, there are none from a nuclear vessel. But the rest of the Russian ice-breaking fleet, which is substantial, and all the commerce that's going through there, and the US and the Canadians and the Swedes and everyone else with icebreakers. China had a major expedition this summer in the Arctic. China is building perhaps the biggest icebreaker ever right now. South Korea is building an icebreaker, very interested in Arctic commerce. They're burning the lowest, sort of most useless, otherwise grade of oil. Can't be used for anything else in their ships, bunker oil. So this puts a lot of soot in the atmosphere. Now the Crystal Serenity claimed that they were not using these low-grade oils, that on their ship for this transit they were using premium fuels, so we'll give them a little break there. But you have ships, you also have air transport. And it isn't something you usually think about. You see an airplane flying overhead, and you don't see a black smokestack like a city bus like we used to have in Boston. We don't anymore. They used to be on diesel, now they're on natural gas. But you go to many parts of the world, you still see a guy plume out of a city bus or a truck. Well, airplanes are also emitting small particles of carbon, and there are people who have argued that the contribution of aircraft carbon to accelerating Arctic melt is non-trivial. Some people disagree with that, but it is interesting that of course, none of you in this room would really remember it, but before the end of the Cold War, before the Soviet Union dissolved after the 1989 collapse of the wall in Berlin, there was no aircraft traffic over the Arctic, zero. Any airplane flying over the Arctic was an incoming bomber or had something that was going to set off all kinds of alarms. Today, of course, aircraft crisscross the Arctic every day from every direction. We also have winds that transport black carbon to the Arctic from lower latitudes, and some of that not only from diesel and the like, but some of it also from forest fires. And whereas we could control the emissions on a lot of these internal combustion engines, forest fires are not only more difficult to control, but they may become increasingly common in the Arctic. So there are people who have actually argued that one of the ways to slow the melt in the Arctic, and particularly when you look at the dark aggregations of this material that's called criconite that you see on glacial surfaces in Greenland under a bit of meltwater, and here the water will, as one of James Balog's photos, will tend to move this material around and see it aggregating in these cracks. This effect is again tied to the black carbon aggregations that are collected then with movement of water over the surface. But there are a lot of sort of interesting work being done with this now, looking at the role of microbes as important constituents in the formation and maintenance of the criconite. So there's some big questions there, but it's an active area of research. And people have also argued, and quite, I think, convincingly, that if we were to work on these short-lived greenhouse gases and other radiative forcing agents like black carbon, which doesn't stay in the atmosphere for a long period of time, like CO2, it's going to certainly rain out gravity or with precipitation. And of course, methane, another short-lived greenhouse gas that we could do a lot more to control the sources of. That if we worked on some of these short-lived radiative forcing agents, we could conceivably slow this current pace of melt in the Arctic. So I'm going to shift a bit now. Janet asked if I might say something about some of our whale work, and then touch on that, but then link it back to the importance of high latitude. So with Joe Roman, a former student, we've been looking in the last handful of years at how different marine ecosystems are after the loss of substantial populations of the great whales that were extracted in the commercial era. And of course, the grand creature in the ocean, the blue whale, 100 to 120 tons, and particularly in the Antarctic circumpolar region, was just one of the most tragic stories of this whale depletion. If we look at the blue whale, estimated population removal, rather, of about 340,000 individuals by the whaling effort, and its recovery today in the Antarctic is only about 1%. So we're missing this big component of the ecosystem. Fin whales have recovered only to about 40%, 14%. Humpbacks maybe 30%. And there in some areas, some localities, these whales have done better than others. And of course, if you think about what we did with these whales, we burned that oil for illumination, and also baleen. So whales are still being harvested by indigenous communities, but with a lot of regulation and very responsibly. They consume all the whale. Whales are not harvested in excess of what they can use, very strictly regulated. And in some parts of the world, of course, that's not true. Japan and Iceland and Norway continue to whale for market consumption, which is arguably not really essential the way it is for subsistence livelihood. Japan has years of whale flesh stockpiled in freezers right now, and yet they continue to harvest whale. whale is not being consumed by younger people in Japan the way it was by their parents and grandparents. So Joe Roman and I argued that whales actually enhance productivity in coastal waters. And it's again the opposite of what some whaling nations have argued. The whales are competing with us for fish. They eat our fish. In some places they do. That's true. But our argument is that the whales actually, by diving to depth and feeding, coming back to the surface where they do all their digestion and excretion, and you may or may not know, it's not too close to dinner time, I guess, but whale poop is like really, really bad diarrhea. It's just this cloud of brown, or here you see the crustaceans that are eating left a reddish color, and this dissipates very rapidly. And so it doesn't sink. Like this little copepod here makes a dense little fecal pellet that sinks at hundreds, maybe 1,000 meters a day, so it's gone. Whereas the whale fecal material stays in the surface, and so actually retains nutrition for microbes and phytoplankton in the surface water. The other interesting part of this, we've worked with Andy Pershing and others, is how, and it's the metabolic scaling argument, the impact of whales is very different than the same amount of biomass of another organism, smaller organism that's eating the same food. So you know that with a larger animal, is the animal size here, mass, the rate of metabolism goes up. The elephant has a higher rate of metabolism than the frog, and it doesn't matter whether you look at warm-blooded, cold-blooded, or microbes, you get the same relationship. And so you have this scaling factor, but the one that is really important is that the large animal consumes less, consumes less oxygen, or consumes less carbon per unit mass than the small animal. Its metabolic rate is lower. So what it means is more of what it consumes goes to growth and reproduction, and less to respiration. And you see that here. So here's the elephant, and here's the shrew. That's kind of extreme, but you go down to a smaller animal here. So you can see over this range of size, the smaller animal needs more food to meet its energetic demands than relative to its biomass than the larger animal. And here's a cartoon version of what that would mean for the blue whales that we were talking about. So here's the abundance of blue whales. So let's say 300, here's our 300,000 that are missing now from the Antarctic circumpolar region. That same number of blue whales were its food to have gone to a smaller whale, the minke, or take the penguin here. Rather than having 300,000 blue whale, that same amount of food would produce something that's up about 500 million, or 500, say 10 to the 8, 10 to 6 million, 500 million penguin. So you'd have a lot more penguins. However, because the penguin has a high metabolic rate, a larger portion of what it consumes gets respired, thrown back as CO2 to the atmosphere. Of course, penguins put their poop on rocks and makes this awful gooey mess up there, but rather than the water. But if you look at over here at biomass, you can see that the biomass of that amount of whale is about 10 times 3 in the scale of 10 to the 7th tons versus 0.3. So it means that more of what the whale consumes is contained in the whale tissue, and then what it does metabolize and gets released in the water column, rather than a smaller fraction of what's consumed in the tissue. So the whale's holding more of that carbon and nitrogen in its system, and what it isn't holding, it makes available in the adjacent water. Now, here's how this ties back to high latitude regions. These whales, like the seabirds I mentioned earlier, don't stay in one place year round. They feed in the high latitude regions. They feed where these Arctic and Antarctic ecosystems are very productive in the summer season. And then they migrate to calve to lower latitude, from the north to temperate latitudes, from the south to temperate latitudes. So they export nutrition from the high latitude regions in the form of milk and lipid that makes more milk for the calves that are born in these temperate regions. So we published a paper a couple years ago, which we called Whales Marine Ecosystem Engineers, and listed ways in which we think that their importance as in shaping ecosystems has been underestimated. And the final point down here at the bottom, the continued recovery of great whales may help to buffer marine ecosystems from stabilizing stresses, and could lead to higher rates of production localities where whales aggregate to feed and give birth. So this, again, takes us back to the importance of those high latitude regions, and as they change, as we're seeing them change, the capacity of the Arctic to provide the nutrition for whales will be diminished. So I like the end of the cartoon. This is from the New Yorker a few years ago that I thought was particularly moving. You'll recognize the guy in the Pequod boat here that we have. And with that, I'll conclude. Thank you.